Tonight, somewhere above you, the moon is moving, not in any way you can feel. About 1.5 inches further from the Earth this year, a little further next year, a little further the year after that. 4.5 billion years ago, it was so close that it filled the sky. And before that, it was not there at all. Most of the things in the night sky are very far away. The stars are unimaginably distant. The planets are tiny points of light drifting on their own slow orbits. But the moon is close. The moon is so close on a geological scale that it is almost touching us. And it has been with us, in one form or another, for nearly the entire history of our world. We have lived our whole lives under that pale gray light. Every story we have ever told, every harvest we have ever counted, every tide that has ever risen and fallen has happened beneath it. It is so familiar that it can feel ordinary. But it is not ordinary. It is one of the strangest, most unlikely things in the inner solar system. And it was born in a single afternoon of unimaginable violence out of an event that almost destroyed the Earth. This is the story of where it came from, the story of the world that no longer exists, the world that became the moon, the story of the day the sky changed forever, and the story of what that pale companion has been quietly doing for our planet and for life ever since. So settle in, let your shoulders ease. We're going to travel slowly, the way the moon itself travels, back through the long quiet of geological time to a younger sun, a younger Earth, and a moment older than every stone. To understand why the Earth has a moon, it helps at first to look at the planets that do not. Mercury, closest to the sun, has no moon at all. It is a small gray world, scoured by solar wind, baked on one side, frozen on the other, and entirely alone. There's nothing in its sky but the slow turning of the stars and the brilliant, oversized disk of the sun. Venus, our nearer neighbor, also has no moon. Venus is almost the same size as the Earth. It has a thick atmosphere, a slow rotation, a surface hot enough to melt lead. And yet, it is moonless. The Venusian sky has never known a second light. Mars has moons, but they're not really moons in the way that ours is. Phobos and Deimos are small, irregular lumps of rock, only a few kilometers across, more like captured asteroids than companions. From the Martian surface, Phobos looks like a small, dim potato passing overhead. Neither of them does anything for Mars. They do not stabilize its tilt. They do not raise meaningful tides. They are decorations, not partners. This is the inner solar system, 4 small rocky planets and one ordinary set of arrangements. No moon, no real moon. And then the Earth, our world, with a companion fully 1/4 of its own diameter. A companion so large that, when seen from far away, the Earth and the moon look almost like a double planet, a binary system orbiting the sun together. There's nothing else like it among the inner planets. Among all the worlds that wheel around our star, only the Earth has a satellite of this scale, this proportion, this character. And once you see that, the question begins to feel less like an idle one and more like a mystery. Because if moons of this size were normal, surely Venus would have one, or Mars, or Mercury. They had 4.5 billion years to acquire one, and they did not. So the moon is not a default feature of being a rocky planet. It is something else. It is the trace of a particular event. A particular accident, very early in the history of the solar system, that happened to the Earth and to no one else. To find that event, we need to travel back, all the way back, to a time when the sun was younger, when the planets were not yet finished, and when the inner solar system was a far more crowded and far more dangerous place. 4.5 billion years ago. It does not look like the Earth. There are no oceans. There are no continents, there is no blue, there is no green. The atmosphere, if it can be called that, is a hot, hazy fog of hydrogen and helium and the steam of vaporized rock. The surface is glowing. Vast oceans of molten silicate stretch from horizon to horizon, the rock itself behaving like a liquid because it is too hot to be anything else. The surface temperature is well over 1,000 degrees Celsius. The young sun, smaller and dimmer than today, hangs in a sky that is not yet blue, and its light shimmers across waves of glowing magma. This is the Earth in its earliest infancy. A hot, glowing, mostly molten ball, still being assembled, still being struck day after day by the smaller bodies of rock and iron and ice that were the leftover material of planet formation. The Earth at this point was not finished. It was about 90% of its present mass, perhaps a little more. The last 10% was still arriving, slowly, piece by piece, in a long rain of impacts that lasted for tens of millions of years. Above the molten surface, there was no moon. There was no companion in the sky. There was only the sun and the slow turning of the stars and other planets in the distance, themselves still glowing from their own formation. Mercury was newly forged. Venus was a hot twin, much like the Earth, though without an oxygen-bearing future. Mars was smaller, finishing more quickly, already cooling toward a thin atmosphere it would eventually lose. But the inner solar system was not just 4 planets and the sun. It was crowded. Astronomers now think that in those first 100 million years, there may have been many more rocky bodies than there are today. Embryos, protoplanets, half-finished worlds, some as large as Mars, some smaller, all on their own orbits, all gradually colliding, sticking together, or being thrown out of the system entirely. The early solar system was a shooting gallery. It was a storm of stones, slowly resolving itself into the 8 planets we know now. And in that storm, there were collisions, not the small, occasional cratering events that we still see today on the surface of the moon, but true collisions. Whole worlds striking whole worlds, bodies of planetary mass meeting and merging and sometimes shattering. We know these things happened because the planets themselves carry the evidence. Mercury is unusually iron-rich, possibly because its outer rocky layers were stripped off in an early impact. Uranus is tipped on its side, almost certainly because something the size of an Earth hit it long ago. Venus may have been spun backwards by another such event, and the Earth, in this same young, violent system, was waiting for its own great encounter. It had no idea as a glowing ball of magma what was coming for it, but the geometry of the solar system had already drawn it close. The world that was coming had a name, or rather, we have given it a name long after the fact. We call it Theia. Theia, in the old Greek stories, was the mother of the moon, the Titaness whose daughter Selene drove the silver chariot across the sky. It is a fitting name because, in the modern story we are about to tell, Theia is the world that became the moon, or at least the world that, together with the Earth, became the Earth and the moon as we know them now. Theia was probably about the size of Mars, roughly half the diameter of the Earth, a small rocky planet in its own right, with a metallic core and a silicate mantle, finished or nearly finished, fully formed enough to be called a planet. It had a crust. It may have had a thin atmosphere of vaporized rock and hot gases like the proto-Earth. It almost certainly had no liquid water. It had no life. It had no name, and no observers, and no awareness of any kind. It was simply a small rocky world drifting on its own orbit about 93 million miles from a young sun. For a long time, Scientists puzzled over where Theia could have come from, because if Theia had been on a wildly different orbit, on a steep angle compared to the Earth, the impact would have left a different kind of signature. The Moon and the Earth, when we measure their oxygen isotopes, the chemical fingerprints of where in the solar system a body formed, turn out to be remarkably similar, almost indistinguishable. They share something, some deep chemical likeness that says they were made out of similar starting material. That likeness was, for a long time, a problem. Because if a Mars-sized body from somewhere very different smashed into the Earth and made the Moon, you would expect the Moon to look chemically distinct from the Earth. So either the impactor came from somewhere very nearby, with very similar starting material, or the collision was so violent that the two bodies completely mixed. One promising answer is that Theia formed at the same orbital distance as the Earth, sharing the same lane around the Sun. There are gravitationally stable points in any orbit, called Lagrange points, particular spots 60 degrees ahead and 60 degrees behind a planet where another smaller body can sit in a kind of resonant balance. It is possible that Theia grew quietly in one of these points, a second world sharing Earth's orbit, slowly fattening on the same debris made of much the same material. For tens of millions of years, perhaps, the two worlds circled the Sun together, two ovens, two glowing half-molten balls unaware of each other, pulled by the same gravity, basking in the same light. The Earth on one side of the Sun, Theia in its quiet stable point on the other, or just behind or just ahead. Recent work, including studies published in 2025, has revisited this picture. Some researchers have proposed that Theia carried a particular kind of carbon-rich material from the outer solar system, material that the Earth had not yet absorbed. Others have studied in fine detail the chemistry of certain elements that should not have evaporated easily, refractory elements, and asked whether the standard story of the impact can really explain everything we see in the lunar rocks. The picture continues to be refined. The exact mass of Theia, the exact angle of its approach, the exact temperatures inside the colliding bodies, all of these are being adjusted as new measurements come in from the Apollo samples and from new computer simulations. But the broad shape of the story has held up for nearly half a century. Sometime in the first 100 million years of the solar system, Earth and Theia, two worlds on similar orbits, drifted toward each other. The gravitational balance that had kept Theia in its quiet corner began slowly to fail. And we do not know what the last morning was like on the proto-Earth before the impact. There were no mornings exactly, because the day was much shorter then, and there was no atmosphere of the kind that scatters blue light. The sun rose smaller and dimmer than we know it. The sky was a dull, hot orange, full of vaporized rock. The molten oceans hissed and churned. There were no clouds in the modern sense. There was only steam and ash, and the heavy weight of an atmosphere of vaporized silicate. Theia, by this point, was approaching. From the surface of the Earth, if there had been anyone to see it, the other world would have first appeared as another small bright disk, somewhere among the wandering points of light. Then, over years and centuries, or perhaps over only weeks, depending on the geometry of the final approach, it would have grown brighter, then resolved into a glowing orb, then into a half-disk, then into a world hanging in the sky, larger than anything any later eye would ever see in the heavens. The collision, when it came, was not head-on. The simulations that best match the chemistry of the present-day Earth and Moon suggest a glancing blow. Theia struck the Earth at an angle, perhaps somewhere around 45 degrees, at a speed of around 4 kilometers per second, which sounds modest, but in planetary terms an enormous closing velocity. Two worlds, each made of millions of tons of rock, meeting at the speed of a fast bullet. What happens in such a collision is unlike anything in our daily intuition. The two worlds do not bounce, they do not crack like glass, they flow into each other. The energy of impact is so vast that the rock itself ceases to behave like a solid. Both bodies at the contact point are vaporized almost instantly. Behind that vapor, deeper into both worlds, the rock begins to flow. The cores of the two planets are still solid, the iron and nickel at the center of each. But their mantles, the outer layers, melt and surge. In some simulations, the impact takes only hours. NASA scientists using high-resolution computer models have shown that the entire collision and the formation of an orbiting cloud of debris around the Earth could have happened in less than a day. A planetary collision compressed into the time it takes for a single sunrise. In those hours, the Earth itself was nearly torn apart. A vast plume of molten rock and vapor was thrown into space, not a thin sprinkling. A great, hot, glowing arc of debris, perhaps a few percent of the mass of the original Earth, possibly more, was launched outward. Some of this material flew away forever, lost into deep space, scattered onto orbits around the sun. Some of it crashed back down onto the proto-Earth, adding its mass to ours. And some of it, the lucky middle fraction, went into orbit. Theia itself ceased to exist. Most of its iron core, the dense center of the destroyed world, sank straight down through the molten Earth and merged with our own iron core. So somewhere far below your feet, under the mantle, in the heavy heart of the planet, there is metal that was once the heart of another world. Theia did not vanish. Theia became part of the Earth, and much of Theia's mantle, its rocky outer shell, joined the Earth's mantle, fully mixed. There are now ideas, supported by simulations from the early 2020s, that two large, unusual structures deep in the Earth's mantle, the so-called large, low shear velocity provinces, may be remnants of Theia's body, still distinguishable, still drifting, still slightly different in composition deep below the surface. Whether or not that turns out to be the final answer, the broader truth is unmistakable. The Earth that you live on now is not pure Earth. It is the Earth plus most of Theia mixed together. We are walking on the merged remains of two worlds. But not all of Theia and not all of the outer Earth fell back. Some of it stayed in orbit, and out of that glowing ring of debris, something new was about to be born. In your mind, the Earth in the hours and days after the collision. The atmosphere, such as it was, has been blown off. The surface is a single global ocean of liquid rock, white-hot, steaming, glowing. The sky is no longer there in any meaningful sense. There is only space, beginning a few hundred kilometers up, and beyond that, a slowly cooling cloud. Around the wounded Earth, a disk has formed, a ring of vapor and droplets and chunks of partly molten rock. Some of this material is so hot that it is gaseous, silicate rock vaporized into a thin, glowing atmosphere of metal oxides. Some of it is fine spray, like a furnace mist. Some of it is rocky lumps the size of mountains, tumbling end over end, tracing wide arcs through the disk. The disk is bright. If you could stand on the moon today and look back at the Earth as it was then, you would see the Earth ringed in a glowing band, brighter than anything our planet ever shines now. From above, looking down at the system, the Earth and its disk would have looked almost like a small, hot miniature Saturn. In this disk, gravity goes to work. The hottest, lightest material, the silicate vapor, does not fall back to Earth. It hangs at a particular distance where centrifugal motion balances gravity. The denser droplets begin to settle, they cool, they collide, they stick, they make larger lumps. The lumps draw in more droplets. Larger lumps draw in smaller ones. Within decades, perhaps a few centuries, the disk begins to resolve into a small number of large bodies, and then those bodies in turn swallow each other. There is, in this process, a quiet sort of inevitability. A disk of orbiting debris cannot stay a disk forever. The various pieces are all on slightly different orbits, with slightly different speeds, and so they collide. Each collision either sticks two pieces together or it shatters them. Over time, the sticky collisions win. Mass concentrates. The disk thins. Smaller bodies are absorbed into the largest one, and gradually, the orbiting cloud is replaced by a single growing, glowing world. There's also a particular line in space around any planet called the Roche limit. It is the distance inside which the planet's tidal pull is so strong that no body held together only by its own gravity can survive. Closer than the Roche limit, a forming moon would be torn apart by the very planet it orbits. The lunar disk, once it cooled, organized itself just outside this line. There, the pieces could finally find each other and begin to gather instead of being constantly pulled apart. We do not know exactly how many small intermediate moons formed and collided before the final body emerged. Some simulations suggest two large lumps that later merged. Others suggest a more gradual gathering. There may have been a phase when the Earth had two small moons in the sky at once, briefly, before they joined. Or perhaps it was always one. Whatever the precise history of those first centuries, the end result is what we see now. One moon. The disk resolved itself into a single body, and the single body settled into a roughly circular orbit and stayed. The whole process is, by the standards of geology, astonishingly fast. Where the Earth itself took tens of millions of years to assemble out of the dust of the inner solar system, the moon assembles out of the disk around the Earth in something like 100 years, perhaps a few hundred, perhaps less. The exact figure depends on the simulation, on the disk temperature, on the distribution of material, but it is, in cosmic terms, an instant. By the end of that interval, where there had been a glowing ring, there is a single body, a young moon. It is nothing like the cold, gray, cratered companion you can see tonight. It is a glowing ball of molten rock. Its surface is a single global magma ocean. It is hot enough to glow visibly. It hangs in the sky just above the Earth, far closer than today, perhaps as close as 20,000 or 30,000 kilometers, which is roughly 1/12 of the distance the moon orbits at now. From the surface of the Earth, if you could have stood upon a steaming ridge of cooling rock and looked up, the moon would have filled an enormous portion of the sky. Not a small disk the width of your fingernail at arm's length as it is now, but a great, glowing, threatening face, perhaps 15 times the angular size we see today. The whole sky on the side facing it would have been bathed in red and orange light. There is no night in the modern sense. The moon at that age was a second, smaller sun hanging low, drifting slowly across the heavens, and both worlds, the Earth and its newborn moon, were still rotating very fast. Calculations suggest the day on the early Earth was perhaps only 5 hours long, possibly less. The moon, locked in orbit, swung around the planet correspondingly quickly. The whole system, the spinning, glowing Earth, the spinning, glowing moon, the merged metal cores below, the boiling magma seas, was a dynamo of energy, slowly winding down, slowly cooling, slowly settling into the more orderly system we live in now. The first moon was molten. Its surface was a global ocean of magma, perhaps several hundred kilometers deep. It glowed in the sky like a second, smaller sun. It had no craters yet because the surface was liquid. Anything that struck it simply splashed in and was absorbed. It had no maria, no highlands, no mountains. It had nothing of the geography you might recognize. It was a smooth, hot, liquid sphere. But cooling in space is relentless. Heat radiates outward into the cold of space, and there is nowhere for the warmth to hide. So the moon began to cool. From the surface inward, slowly, the magma ocean began to crystallize. The lighter minerals, the bright white minerals called feldspars, the kind we now call anorthosite, floated upward through the molten rock. They gathered at the top. They formed a thin, light, rocky crust. The denser, darker minerals sank. Below the white floating crust, an iron-rich mantle settled. The moon began to differentiate, just as the Earth had. The very oldest rocks we've ever brought back from the moon, the rocks the Apollo astronauts walked across, lifted and placed in their sample bags, are pieces of this primordial highland crust. They are about 4.5 billion years old. They are some of the oldest pieces of any solid surface in the inner solar system that we can hold and examine. They are lighter in color than most of the rest of the moon. And that bright color is the reason the moon shines as cleanly as it does in the night sky. We are seeing the first crust. We are seeing what floated to the top when the moon was still a sea of molten rock. Below that bright crust, in places, there were still pools of molten interior, even after the surface hardened. Heat from the great impact, plus the heat from the slow decay of radioactive elements like uranium and thorium, kept parts of the moon warm for a very long time. From those warm pools, dark basaltic lavas would later well up, flooding the low spots, the great impact basins formed by later collisions. Those dark plains we call the maria, the seas, although they hold no water. They are frozen lavas, smooth and dark, that we can still see from Earth as the gray patterns on the face of the full moon. Above the cooling moon, the Earth itself was also cooling. The blow from the impact had thrown most of the original atmosphere into space. The remaining hot vapors condensed. Steam fell eventually as rain. The rains lasted in fits and starts for ages until the first oceans gathered in the lowest places. The crust hardened. The first true continents began to form, perhaps not yet recognizable, but beginning. The Earth was becoming the Earth. And all the while, the young moon was overhead, closer than today, larger in the sky than today, cooling, brightening, slowly fading from a red-orange glow to a more familiar pale gray-white as its crust thickened and its lavas froze. The two worlds, parent and child, settled into their long companionship. The moon, once it had cooled, did not just hang there. It tugged on us, and we tugged on it. And that mutual tugging, that two-way gravitational handshake, has been one of the most quietly important forces in the history of our planet. The most obvious effect of the moon, the one anyone can see at the seashore, is the tide. The moon's gravity pulls on the Earth, and because the side of the Earth nearer the moon is pulled slightly more strongly than the far side, the planet itself is gently stretched. The oceans, being free to move, respond first. They bulge outward on the side facing the moon and on the side directly opposite. As the Earth turns under those bulges, the bulges remain pointed at the moon, and so we experience the rhythm of high tide and low tide twice each day, almost everywhere along the coasts of the world. We tend to think of tides as a fairly small thing, the level of the sea rising a meter or two, depending on where you live. But the tides 4 billion years ago were not small. With the moon so close and the day so short, the tides were enormous. Some calculations suggest tidal ranges of hundreds of meters, possibly kilometers, in the open early ocean. Whole regions of the early seafloor would have been alternately flooded and exposed several times a day by tidal motions of unimaginable scale. Many scientists believe that this great rhythm, the daily flooding and uncovering of vast tidal flats, may have played a role in the origin of life. Tidal pools concentrate chemicals. Pools that fill, partially evaporate, and refill again can accumulate organic molecules. They can dry and rehydrate and dry again in cycles. Some early ideas about how the first self-replicating molecules formed lean heavily on this kind of tidal cycling. Without the moon, those cycles would have been weaker, perhaps still present due to the much smaller solar tide, but weaker, less varied, less likely to drive the chemistry forward. Picture for a moment those early shores, the light of a younger sun, a close, looming moon, larger in the sky than any modern eye has ever seen. And below, an ocean rising and falling in vast, slow breaths. Not the gentle meters of today, but tens or hundreds of meters at a time. The water sweeping in over flat black basaltic plains, then drawing slowly back, leaving long stretches of glistening rock, leaving pools of warm salty water, rich with dissolved minerals. The air above thick with carbon dioxide and water vapor. No green anywhere. No sound of birds because there were no birds, and no insects, and no reeds. Only the slow heave of the sea and the patient cycling of those tidal pools, drying and refilling for hundreds of millions of years. Somewhere in that long, slow rhythm, in some particular pool, on some particular shore, the first self-copying chemistry may have begun, or it may have begun elsewhere, on the deep sea floor by the warm vents. We do not know for sure. But the moon's tides, vast and ceaseless and ancient, were almost certainly part of the chemistry that the early Earth was running. The tides also do something else. Slowly, almost imperceptibly, they slow the Earth down. Each tidal bulge, as the Earth spins under it, is dragged a little ahead of where it should be. The moon's gravity then pulls back slightly on that bulge, and that pull acts as a tiny, ceaseless brake on Earth's rotation. The result is that the Earth is spinning more slowly than it used to, by a measurable amount. When the moon was newly born, the day on Earth was perhaps 5 hours long. By the late Cambrian, 500 million years ago, when complex animals were evolving, the day had stretched to about 21 hours. 200 million years ago, in the time of early dinosaurs, the day was about 23 hours. Now, the day is 24 hours, and it is still lengthening. Slowly, by tiny fractions of a second each century, but unmistakably. And that energy that the Earth loses in its slowing rotation has to go somewhere. It does not vanish. It is transferred by the same gravitational handshake to the moon. The moon accelerates very slightly in its orbit, and as it accelerates, it climbs to a higher orbit. That is why the moon is moving away from us. About 3.8 centimeters per year. There is roughly the rate at which fingernails grow, and it is perhaps the most important, very slowly, even though it is the one we feel the least. The Earth spins on a tilted axis, about 23.5 degrees off the perpendicular. This tilt is the reason we have seasons. As the Earth orbits the Sun, the northern hemisphere leans toward the Sun for half the year, and the southern hemisphere leans away, and then 6 months later, they switch. That is summer and winter. That is the long rhythm of monsoon and dry season, of breeding and migration, of the year that every culture on Earth has built its calendars upon. But that tilt is not naturally stable. The Earth, spinning alone, would be a kind of slow gyroscope susceptible to gravitational nudges from the other planets. Jupiter, the giant, with its massive gravity. Venus, our nearer neighbor. Saturn, even Mars. All of them tug on the Earth's spin axis in subtle, complex ways over very long times. If left to those nudges alone, the Earth's tilt would not stay neatly at 23.5 degrees. It would wander. We know this because we can see what happens to a planet without a stabilizing moon. Mars, in the simulations, has a tilt that has wandered wildly. Mars's axis has, in the past, tipped over by tens of degrees. It has, on long timescales, pointed almost directly at the sun. When that happens, the polar regions become equatorial, the equator becomes polar, and the whole pattern of climate is shaken to its foundations. Mars is dry now, in part because its axial chaos, combined with its low gravity and lost atmosphere, has prevented it from holding any kind of stable climate over geological time. In the early 1990s, the French mathematician Jacques Lascar and Philippe Robutel showed that the Earth, without its large moon, would behave the same way. The Earth's tilt would wander. In some long simulations, it would wander by 60 degrees or more. The poles would swing toward the equator. The equator would tip over toward the poles. Ice ages would not come and go in tidy 100,000-year cycles. They would come in jagged, unpredictable, planet-wide convulsions. Some regions would freeze for ages. Others would scorch. The moon, by orbiting the Earth at 1/4 of our diameter, by being so unusually large for a satellite of an inner planet, provides a steady gravitational anchor. The moon's pull on the Earth's equatorial bulge counteracts the slow, chaotic tugging of the other planets. It holds the gyroscope steady. It locks our tilt to within about 1 or 2 degrees of its current value over the longest timescales we can probe. It gives us a climate that varies but does not rage, a climate in which forests can grow for tens of millions of years, a climate in which complex animals, slow to evolve, can keep evolving without being scoured off the surface again and again by sudden new ice ages or new desertifications. In a sense, the moon does not just light the night, the moon stabilizes the day. The moon holds the year together. Without it, there would still be a planet here, and there might still be life, and there might still be oceans. But the long, patient calm in which forests have time to mature, in which mammals have time to diversify, in which a single curious species has time to look up and start asking where its companion came from, that long calm is, in part, the moon's gift. There is something almost gentle about this. The moon does not act fast. It does not push. It does not pull dramatically on any given afternoon. It simply hangs there in its slow circle around the Earth, and through the steady, patient pressure of its gravity, year after year, age after age, it keeps the planet pointed in the right direction. It is a kind of long, quiet anchoring, applied across geological time while everything else changes. Continents drift, oceans rise and fall, ice sheets advance and retreat. Forests grow and burn, species emerge and disappear, and the moon overhead just keeps doing the one slow thing it has always done, holding the world steady while the world is busy. It is worth pausing on this. Imagine, for a moment, an Earth without that anchor. Not the Earth of today with all its complexity, but a different Earth that took a different path. A planet whose axis tipped over a few 100,000 years from 23 degrees to 70. A planet whose North Pole, instead of pointing toward Polaris, pointed toward the sun. On such a world, the sun would rise once a year over each hemisphere, and not set for half a year, and then sink and not rise for the other half. Whole continents would have polar nights of months at a time, while the other side baked under unending summer. There would be no familiar pattern of season. The very idea of a year, as we know it, would not apply. Migrations would be impossible. The annual cycle of leaf and flower and fruit, on which so much of life on Earth has built itself, could not exist. Instead, there would be slow, planet-wide convulsions of light and shadow on a rhythm too long for any animal life to tune itself to. That is, in some sense, the Earth we did not get. That is the Earth that the Moon, by its quiet presence, in recent decades, steering us away from. Our picture of the Moon's origin has continued to sharpen. Apollo brought back about 380 kilograms of rocks from the lunar surface, and those rocks have been studied for more than 50 years now. As measurement techniques have improved, the rocks have given up new secrets, slowly, gently, like an old book being read in a different light. We have learned, for example, that the oxygen isotopes of the Moon and the Earth are extraordinarily similar, almost identical. This is one of the constraints that any working theory of lunar origin has to satisfy. If the impactor had come from a wildly different part of the early solar system with different starting material, the Moon should look chemically different from the Earth. It does not. So whatever mixed thoroughly. Either Theia and Earth grew up together in nearby orbits made of the same material, or the energies of the collision were violent enough to homogenize the two bodies completely, or both. We have learned that the Moon is unusually dry, very low in volatile elements, the kind of light, easily evaporated chemicals, water, sodium, potassium, that you would expect to find in a body that grew slowly out of cold dust. The Moon does not have them in normal amounts. It has been baked. Whatever made the Moon was hot enough to drive off most of those volatile compounds. That is a strong fingerprint of an impact origin. It is much harder to explain in any model where the Moon formed slowly and quietly. We have also learned from very recent work in the 2020s that some elements that are not so easily evaporated, refractory elements locked into solid mineral grains even at high temperatures, do not match between the Earth and the Moon as well as we might expect. A 2025 study reported that the lunar refractory composition raises new questions for the simplest version of the impact hypothesis. The Moon is a little too unlike the Earth's outer mantle in those particular elements, which has led some researchers to ask whether the impactor, Theia, was more chemically distinct than we used to think, or whether the magma oceans of the two colliding bodies were already separated into different layers by the time they met, and the Moon ended up biased toward one of those layers. These are not new theories of lunar origin, they are refinements. The broad story, the giant impact, Theia, the disk, the rapid accretion, is now nearly half a century old, and it is held up. But the details, the exact angles, the exact chemistry, the exact mass, are still being worked out. New computer simulations with much higher resolution than was possible even a decade ago can now follow individual lumps of rock through the disk. New isotope measurements on tiny grains in lunar samples can probe the chemistry at finer scales. The story is being polished again and again by patient scientists with better and better tools. And one of the most surprising recent ideas is that pieces of Theia may still exist, intact, deep inside the Earth. There are two enormous structures deep down at the boundary between the Earth's mantle and its core, where seismic waves slow. We call them the large, low shear velocity provinces. One sits beneath Africa, the other beneath the Pacific Ocean. Each is the size of a continent, each thousands of kilometers across, and each chemically distinct from the surrounding mantle. In 2023, a group of scientists put forward the idea that these structures are the remains of Theia, pieces of the impactor that, instead of fully mixing with the Earth, settled to the bottom of our mantle and have been sitting there, almost undisturbed, for nearly the whole age of the planet. Whether or not that idea turns out to be correct, the truth is already strange enough. The world that struck the Earth so long ago did not vanish. Most of it is still here, inside us, around us, above us in the form of the moon. Whenever you stand outside on a clear night and look up, you are looking at most of what remains of a world that no longer exists. You are looking at Theia, slowly continuing its journey. Reformed, recoded, gentled by time, but still made at last back to the moon as it is now. 4.5 billion years ago, pale, came toward the young Earth in synchronous rotation with the Earth, so that one face is always turned toward us and the other is always turned away. Quiet, almost geologically dead. Its volcanism faded billions of years ago. Its surface has been reworked only by impacts and by the slow rain of micrometeorites, not by plate tectonics or weather. It is a museum more than a working world, a museum of the early solar system, preserved in a way the Earth itself can no longer preserve anything. And it is leaving. Slowly. The rate is small, about 3.8 centimeters a year. It does not sound like very much. It is roughly the rate at which your fingernails grow. But it is steady. It has been going on for billions of years, and in each century the moon is a little further away. In each million years it is a few dozen kilometers further away. In each billion years it will have receded by tens of thousands of kilometers. There are limits to this drift. Eventually, far in the future, billions of years from now, the moon will reach a balance point. The Earth's day will have lengthened to match the moon's orbital period. Both will be locked together, the same face of each always turned toward the other, the way one face of the moon already turns toward us today. The whole system will become tidally locked, top to bottom. But that future will likely never quite arrive, because the sun will have changed by then, and the Earth itself will be changed, and the long story of our planet will be entering its later chapters. Long after you, and long after anyone reading these words, and long after every civilization that has ever existed. For now, the moon is still close. Close enough to fill an outstretched fingernail. Close enough to draw the seas up and down twice a day. Close enough to lend its gentle gravitational hand to the Earth's spinning axis, holding our tilt steady, keeping our seasons quietly varied without being chaotic. Close enough to be the brightest thing in the sky after the sun. Close enough, on a clear night, to feel almost like a face. It is easy, knowing the violence of its origin, to think of the moon as something dramatic, the remains of a destroyed world, the scar of an apocalyptic collision. And, in a sense, it is. It is the calm geological echo of one of the loudest events in our planet's history. But that is not how we experience it. We experience it as a presence, a lantern over the sea, a clock on the calendar of every farming culture that has ever existed. A friend, almost, in the long history of human nights. A pale companion that has never been further from us than it is tonight, by a few centimeters, and never closer than it was last night, by the same. A slow, slow drift outward that we will never feel. So tonight, when you go to sleep, the moon is somewhere overhead or somewhere on the other side of the Earth, doing its quiet work, holding the axis steady, drawing the oceans up and letting them down, reflecting just enough sunlight to silver the leaves on a windowsill or the surface of a lake somewhere far away. It does not need anything from us. It does not know we are here, but it has been here, in one form or another, for almost as long as the earth has been here, born out of fire and collision, settling over billions of years into the calm gray light that has watched over every dream that has ever been dreamed on this planet. That is why the earth has a moon. Because long before there was anyone to ask the question, two worlds met in the early dark, and one of them gave itself almost entirely to make the other complete. Sleep well. The moon is in its place, drifting slightly, steady enough, and it will be there tomorrow and tomorrow and tomorrow for longer than any of us will ever know.